Hello, physics students. Today we are going to dive back into Newton's laws to talk about Newton's third law. Many of you have probably heard of this law, but I chose to teach it now because I think it applies more directly to momentum conservation and the principles there. So this is just a good introduction as to why momentum is conserved. And just a little bit more about forces. So many of you have heard about Newton's third law. Every action has an equal and opposite reaction, meaning if I push on the wall pushes back with exact same force. If I take physics pony here and smack physics pony, my hand feels exactly as much force as physics pony does. So force 1 equals negative force 2. So in the example of a baseball and a baseball bat, if I take that baseball bat and smack the baseball, the bat and the ball feel the exact same amount of force at any given time, but they're just in opposite directions. This is the force of the ball on bat, and this would be the force bat on ball. Right? The bat applies a force to the ball in that direction, and the ball applies a force on the bat in this direction. So the forces are the exact same, but and I want to dive into this because I think this is where students often can get confused or have some misconceptions over. If we take a bug and a bus, here I have a big bus, right? And I have a little bug here. And this bug kind of flies and the bus is moving with a high velocity this way, and the bus plows into that bug. What's going to happen? Well, the bus is just going to keep moving and the bug goes splat on the windshield. But when we dig a little bit deeper, what ends up happening is the bug flies this way, and then there's a force applied from the bus to the bug, and the bug is then moving rapidly in this direction with the bus, and continuing to go this way. Well, like Mr. Magluck, that doesn't make sense, that the bug experiences the same force as the bus. Well, yeah, they do, but two distinctly different things happen, one to the bus and one to the bug. So if we think, let's say there's a force of 1,000 newtons. When that bug hits the bus, the bug applies 1,000 Newton force to the bus, and the bus applies 1,000 Newton force to the bug, right? Well, let's look at Newton's second law. If my force has to be 1,000, let's say the mass of the bus is 1,000. What will my acceleration be of the bus? It will be 1, right? If my mass is 1,000, my acceleration has to be 1 to equal the force of 1,000. Okay. Let's even go. Yeah. Let's roll with that because then math is easy. What now? So my acceleration for the bus is 1 meter per second squared. I think that's kind of high for that, but that's okay. This is just an example. This is not real life, but this will give us an idea for what's happening. Well, now look at the mass of the bug. Let's say, again, easy math, let's just roll with this. Let's say the mass of the bug is 1 kilogram. Well, what is now going to be my acceleration for that bug to make 1,000 force? My acceleration has to be 1,000, right? So depending on the situation, we don't notice the bus really slowing down or doing anything different because it just keeps going, right? It's not really that affected by the force because its mass is so big. On the other hand, the bug goes flying, it changes its direction, it was flying this way, the bus smacks in it, now it's going that way at a really high rate of speed. And so it has a huge effect on the bug because the mass of the bug is so small, where the mass of the bus is very large. So the exact same force will do two totally different things to two different objects because one might be very large, one might be very small. Another example, if I jump, would you agree that I am pushing down on the earth? I am applying a downward force on the earth. The earth is also applying an upwards force on me. Well, did the earth just move out of my way? Did I just get the whole earth to move? Not really, right? No. It would appear as if nothing happened to the earth. Well, why is that? Well, the earth is huge in comparison to me, right? I am very, 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 very small in comparison to the earth. And when I apply that downward force, I accelerate and move upwards, but the earth essentially stays still. You could actually do a calculation of this, and I have done this, and it turns out that the earth moves like a fraction of a fraction of a fraction of an atom width. But essentially it doesn't do anything, right? It's not going to move, it's not going to budge because the mass is giant in comparison to the force that I could apply. Hopefully that is helpful in understanding a little bit more about Newton's third law. We'll talk more about this in the next video when we talk about momentum and its conservation. Thanks for watching, and we'll see you next time.